Hi everyone. We are now in the final week of this class in which I will be presenting new content. Next week is the actual final week, but next week will be dedicated to reviewing in preparation for the final. So please look on Top Hat where I have posted some details about how the review will go next week, as well as some details about the final. But the content for this week, so for this lecture and Wednesday's lecture, is about decision theory. And in particular, we're going to be calculating expected value. And today we're going to be looking at how to calculate expected monetary value. And then on Wednesday, we're going to look at utility and how to calculate expected value when we're looking at things not just in terms of costs, monetary costs. Okay, but the easiest way to introduce the calculations of decision theory, which use expected value, is with money, and that's what we're going to be doing today. So I will begin with an introduction to why we should care about decision theory and how it builds on the formal tools that we've covered so far in this class. Then I want to give you the formula for calculating the expected monetary value of an action where there's costs associated with the various outcomes of the action, and the paradigm case of that are gambles. So we'll learn how to calculate the expected monetary value of various kinds of gambles. And then finally, I'm going to give you a quick tip about how to calculate the expected monetary value of gambles where there's a cost to play. And that's just a small tip that it's not obvious, but once I show you that tip, it will make certain calculations much easier. So let's begin. So very often in our lives, we are faced with decisions where we are uncertain about the possible outcomes. So here is an example. Should you stay in this class or drop it? Now, maybe this decision is mute because I think we're probably past the deadline, but suppose that we are still earlier in this semester and you're asking yourself whether you should stay in the class or drop it. So this is a decision that one faces. And what we can do is we can start bringing to bear some of the formal tools from this class by first translating the various alternative actions or acts into our formal language. So we can say that A subscript 1 stands for the action of dropping the course. And then A subscript 2 stands for the action of staying in the course. So A means action. So the idea is that in this decision situation, you have two possible actions, dropping the course or staying in the course. Now for each act, there are several possible outcomes or consequences. So if you stay in the course, you might do well. So the consequence or the outcome of you doing well in the course, let's say it's C1, or you might not do well, and that's another possible consequence of that action, so C2. So we can translate the actions into formulas of our formal language. Then we can also think about what the possible outcomes or consequences are, and also translate those into our formal language. So for staying in the course, there's an outcome of doing well, and there's the outcome of not doing well. Now, if you drop, there's other outcomes. You might miss out on an important requirement. So that's one outcome. Another one is that you might save yourself a lot of time and money. And so we can label these as well. And now to choose the right action in this context, i.e. to choose whether you should do A1 or A2, whether you should stay in the course or drop it, what you have to do intuitively is you have to consider how good or bad each of these consequences is. And in addition, though, you have to consider how likely it is that each consequence is to occur. So there's two things that you have to weight. You have to weight how good or bad each consequence is, but also you have to weight it by how likely they are. So really, really bad outcome won't really speak that much against an action if it's very, very unlikely. and vice versa. Okay, so this kind of reasoning about how to act under uncertainty is exactly what we're going to be learning how to calculate this week. But we're going to begin with being able to calculate the expected monetary value of gambles, because what these gambles will do is let us very clearly assign certain numbers to the goodness or badness of outcomes, and those numbers are just the amount of money gained or lost. But in the lecture on Wednesday, we're going to be talking about how to calculate more generally what action you should take, even if we don't have specific monetary values. Okay, but this example is just a simple example to warm us up to why we're looking at decision theory. But now let's, for this lecture, focus on cases in which we have specific amounts of money at stake, and those are gambles. So here's a very, very simple example of this. You have a free ticket to play a game at the local casino. Now, when you get there, you can choose either the coin game or the die game. So what are these games? Well, the coin game is as follows. So a fair coin is flipped, and you win $1 if it lands heads, and you win $2 if it lands tails. So that is the one game that you can choose to play. Or instead, you can choose to play the die game. And how the die game works is that a fair die is rolled, and you're going to win $3 if it lands 5 or 6, but nothing otherwise. So here you stand to gain more money than is possible in the coin game, but it's also possible for you to lose. It's also possible for you to gain nothing, whereas in the coin game you're guaranteed to gain something. Okay, so there's these various considerations which speak against, for and against choosing either of these games, and the expected value calculations I'm going to show you in this lecture are going to give you a precise way of deciding which game you should play. So intuitively, however, you can take a moment to think about which game you think is better before we dive into the formalism. So here's what our expected monetary value calculations are going to show us. So the first thing is we have to figure out how to formalize the acts and consequences. So A1, let's say, is that you play the coin game. And the first consequence of playing the coin game is that you win $1, and that's a case in which the coin lands heads. But then in the case where the coin lands tails, the other possible consequence, you win $2. Now the other action is playing the die game, and here are the two consequences for the die game. So you win $3 if it lands 5 or 6, or you win nothing and when it lands on any of the other numbers. Okay, so here is our first steps in formalizing this decision scenario. So here again, as I've stressed, it's pretty obvious how good or bad each consequence is. We just think about it in terms of the amount of money gained. Okay, but this is a subtle point which we will return to next lecture, and also was covered in the reading from last week. But putting that aside for a minute, let's just, for a moment, until Wednesday, let's just assume that the goodness is just identical to the amount of money won. But nonetheless, we still have to ask the further question, which is how likely are each of these outcomes for each of these games, okay? So because in the first game we're flipping a fair coin, the probability of either of these outcomes, that you win $1 or win $2, is 1/2, okay? Because the fair coin lands heads half the time and tails half the time. Now, in terms of the die, because it's a fair die, it's a regular die, the probability of the consequence 3, which is that you win $3, is 1/3, and that's because, as we said, you win $3 when the coin lands on a 5 or 6, and that is 2 possibilities out of the total 6 possibilities, and 2 over 6 is the same as 1/3, and then the other 4 possibilities, if it lands 1, 2, 3, or 4, that's 4 out of 6, which is 2/3. So here we see the probabilities of the various outcomes. So now what we're going to do is we're going to learn how to combine these probabilities with these values of each outcome to give an overall value to each of these actions, and then we'll compare that overall number which we're assigned. Okay, but now before I just give you the formula, let me try to give you an intuitive justification for the formula which we're about to see. So our question has been, which of these acts is better? That is, should we play the coin game or should we play the die game? So let's consider what would happen in the long run if you played either game over and over for a long time. Suppose first that you played the coin game over and over many times. So half the time you'd win $1 because half the time the coin will land heads and you win $1 if the coin lands heads. And half the time you'd win $2 because half the time the coin lands tails and you win $2 in that case. So if you played it enough, the average amount you'd win per game is $1.50 because half the time you're winning $1 and half the time you're winning $2. So the average win for each game, each time you play this game, is $1.50. Okay, because $1.50 is halfway between each of the possible outcomes, which are both equally likely. Now let's think about the die game, and what if you played the die game over and over many times? Now, if we think about the probabilities, a third of the time you play this, you'd win $3. And the other 2/3 of the time, you're going to win $0. Okay, because again, when the die lands on a 5 or 6, which is a 1/3 probability, you win $3. But all other cases, the other 4 possibilities out of the 6, you only win 0. So in the long run, you actually only average winning $1 per play, okay? Because you add up a third of $3, so a third times $3, which is $1. But anything times 0 is just 0. So $1 is actually the amount you average to win each game. And now what that means, or what that suggests to us, is that actually it's a better choice to play the coin game even once, because you can expect to win more, because the average amount you'd win per game is $1.50 if you played it many, many times. But with the die game, the average amount you win is only $1, which is less than $1.50. So what all of this means is that the coin game, A1, has a higher expected monetary value than the die game, A2. And so therefore, it seems like you should pick the coin game because you should pick the option which has higher expected value. So let me show you these calculations in a bit more detail. So here we have this operator, which we're talking about the expected value of an action. And what goes in here can be any sentence whatsoever. We'll just be considering simple sentences which correspond to simple actions or decisions or choices, okay? So what we're thinking about the expected value of the action 1, which is in this case playing the coin game. And what we do is we take the probability of each consequence times the amount of money you win in that consequence, and you add those all together. So here, you take the probability of the coin landing heads times the amount of money you'll win in that case, and you add it to the probability of the coin landing tails multiplied by the amount you win. Another way of thinking about this is that what you're doing is you're weighting each of the possible, let me repeat that. What you're doing is that you're weighting the value of the possible outcomes by their probability. Okay, so you think, okay, how good is each outcome? But then furthermore, you have to weight them by how likely it is. And that's exactly what has been done here with the coin game. And now we fill in the probabilities. So 1/2 times $1 plus 1/2 times $2 is $1.5, $1.50. And now the expected value of the die game is again the value of the different possible outcomes weighted by their probability. There should be a times here as well, but that doesn't matter. But simply plugging in the probabilities, when you weight the value of the outcomes by the probabilities, in this case, you get $1. Okay, and then the idea is that the decision you should make or the action you should pursue is the one that has a higher expected value. Okay, and that's what our theory has just told us. Now, in the next video of this lecture, I will give you the formula that I'm applying here in a more general form, and then I'll work through some more examples, and I'll give you a tip for calculating the expected value of gambles where there is a cost associated with the gamble. So in this case, we assume that we had a ticket, a free ticket that allowed us to choose either of these games. But in many cases, we'll consider whether we should play a game that costs a certain amount of money just to play. And so I'll conclude the next video with discussing how to calculate those cases.